So before we get started, I just want to maybe gauge the audience and hear if anybody is working with a big data platform or big data utilities. Anybody raise their hand? Are using big data today? Okay, we got 2. Good, good. So then you're going to learn a lot during this session because we're going to talk about how Microsoft is deploying big data technologies in the SQL Server family. And as we go through this presentation, I really try to make it so that we hit a lot of the business value propositions, how you can use the platform, what it's made for, why we can use it versus a regular database. And as we go progressively through the presentation, it's going to get more technical and more technical. And hopefully by the end of the presentation, you'll be able to understand how APS, formerly known as PDW, how that works internally. And you'll have a deep understanding, hopefully, of how you can use it in your environments today. Okay? So usually we like to start off the presentation and we talk about all the hype that's going on. Certainly, a lot of the organizations and customers I talked to today are facing a lot of challenges in terms of meeting all their business requirements for their data warehouse. And if you talk to any of the analysts, third-party groups, Gartner, Forrester, etc., they all have in different ways of looking at how the data warehouse is changing. It's not going away. Some might say the data warehouse is dead, but what we do see, in fact, for sure, is that the data warehouse is evolving. And the types of requirements that we have are much different than what we saw maybe 10 years ago or 5 years ago. And so when we looked across our customers using the SQL Server platform today, and we tried to understand what are those data warehouse challenges that they're experiencing today in their platform, we were able to really break it down into 5 key areas. And so when we talk about these 5 key areas, the data warehouse challenges that our customers are facing every day, we break them down into these 5 areas. And the first one is around volumes. And this can be detailed through, but I think this is probably the most common one I hear is we have a lot more data coming into the data warehouse, we have an agreement with the business says the data has to be ready by 6 a.m. every morning, and IT is having a real tough time bringing in all these new data sets, bringing in new applications, and having to process them in that same batch window every single night. You can also be with historical data, so a lot of times when I go to my customers, we're seeing that they're purging historical data off the platform. It can be for cost reasons, it can be for performance reasons, but they don't really have a platform that makes it easy to bring all the data together in one place. They have to really think about, are we going to expose that data to the business users, and if we do, how are we going to make sure that the data warehouse is performing? The second area that we see that's a big challenge for our customers in terms of data warehousing is around BI and analytics. And so certainly everybody says they want it faster, 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 they want high-speed performance. But what we're really starting to see is self-service and ad hoc. And what I mean here is you just expose the data to your business users and they can ask whatever question they want of it. Now traditionally, IT has tried to figure out what questions is the business going to ask. Where do I need to make the database performant? And so we'll figure out, well, maybe I should put an index on this column. Or maybe I should put an index there. Or maybe I should architect these tables in such a way to deliver that performance. And so it becomes very hard to do this self-service or ad hoc because you don't know what questions the business is going to ask for that data. How do you put an index on one of those columns? You don't know what column you're going to use. The next area we saw is around real-time queries and loads. And this is basically talking about how do I have a platform where I'm not doing nightly batches anymore, but I'm loading data throughout the day. I'm loading data every single hour. And I want to be able to actually query that same data that's being loaded in real time on the same platform. So that's loading and queries happening simultaneously. And the last big area that we see in BI and analytics is moving away from this aggregation concept, right? Business users want to have the ability to drill down to the data. They want to have access to all the data. And a lot of times we're starting to see that these aggregations or these queue builds are taking a really long time in terms of exposing that data to the users. And so I have customers saying, I don't even want to do queue build, I don't even want to do aggregations at all. Okay? Now the third area that we see in terms of these data warehouse challenges is big data, right? And it's not the whole challenge, it's just one of the challenges. And let me be clear about big data. It's not semi-structured, unstructured, all this stuff. Actually, I don't believe there's really any unstructured data unless maybe there's white noise or something, right? I mean, the closest we have to unstructured data is maybe a video file. That video file still has structure on it. So when we talk about big data, I'm not necessarily talking about semi-structured or unstructured. What I'm talking about is data that doesn't go easily into a database. And this can be for a number of reasons, right? It can be big data because the data is coming in very quickly and our database can't load data that quickly. It could be big data because the data doesn't come in tabular format. It's not delimited in rows and columns, and so for you to actually load it into the database, you have to figure out what the structure is of that data. So there's many different types of data, but we see even big data that's very structured. So it's not necessarily always semi or unstructured. But the key here is that it's difficult to get into a database. And so there's other platforms that make it easier to put that data into the platform and also analyze it. The fourth area that we see for our customers is around the design. Many times when we go in and we evaluate customers' data warehouse architectures, they're leaving inefficiencies on the table in terms of getting the performance out of the platform, and that's being able to marry the hardware software together. There's a lot of times I go into a customer, and this is more on the old DB side, but they're looking at their SQL Server database and they're saying, well, I swear the SAN's giving me that many ops, I'll have to go back and talk to the infrastructure team. Maybe we're sharing somewhere, maybe there's a shared resource somewhere on the stack. So what we really look at is how do we take away this obstacle that our customers have in terms of design. When we talk about design, it's really marrying the hardware and the software together. And the fifth area, which Microsoft loves, is Azure. This is the cloud. And if you think about the extensibility of your data warehouse today, being able to expand that out to the cloud easily, today it isn't as easy as you think in terms of moving the data back and forth. Sure, we have platforms in terms of test and dev and fault tolerance and being able to move SQL Server instances across the cloud and on-premises. But when you start to talk about analytics, you talk about large data sets and pushing those on-premises and off-premises, it becomes much more difficult with your traditional database system. So now you have the 5 data warehouse challenges. And I'd like to talk about what our solution is. What is APS, Analytics Platform System, to address these challenges that we're seeing for our customers? And so you say, well, why would you even create APS? We've got SQL Server does an ungodly amount of things. Why would you even, create an APS? And the reason we created APS is really for those 5 data warehouse challenges. We want to focus on specifically data warehousing. So when we looked at data warehousing, we said, as this platform evolves and changes, there's really 2 types of data sets that our customers are going to want to manage and deliver analytics against. And the first data set is relational data. The second is the non-relational data, the big data or the Hadoop. And when we talk about the analytics platform system, this is it. It's that box. And within that box, APS, you have 2 separate platforms. You have your relational data platform. This is built on Microsoft SQL Server technology. And you have your non-relational data platform. This is built on Hadoop. Now, the key that we have within the APS technology is what you see here in the middle. This is Polybase, and this is really what we would consider the flagship technology inside of the APS appliance. And what we've done with Polybase is we've said we're going to take the T-SQL query engine, and we're going to extend that out to Hadoop systems, and we're going to extend out that T-SQL query engine to the cloud. So that our business users, our tools, our DBAs, all of these people that are building on the SQL Server platform can use the same syntax, the same technology, but expose this data in different platforms outside of SQL Server. And when we talk about it more specifically, we're using parallel data warehouse for our Microsoft SQL Server technology. We're actually using the same code base as Microsoft SQL Server, but we've extended that code base out to a massively parallel processing architecture, MPP. And so now we're able to run a single instance of SQL Server across multiple physical nodes. Now this is not sharding. We actually have a parallel aware optimizer that knows about all the data distributed across these nodes and is actually coming up with a parallel query plan to satisfy these queries. And as we go deeper into the presentation, I'll show you exactly how that works. So let's take an example. And this is a global retailer. They purchased the APS platform for a lot of the same reasons that I covered in terms of data warehouse challenges. And let's walk through and see what they had before in terms of their big data architecture, what their challenges were, and why they moved to the APS platform. So you see here that the customer is using Hadoop today, and there wasn't too many folks in the room here that are using Hadoop, but just to give you a little bit of background, a lot of customers that are using Hadoop today, they use it, the buzz term is data lake. And they call it a data lake because they say it's this box and data from everywhere in your organization can go into Hadoop. I don't have to put a schema on it. It's basically copying the file from one directory to another directory. That's essentially how Hadoop is. It's a file system, a parallel one. And so this global retailer was using the Hadoop platform, and they were doing online sales and on-premises brick and mortar. And they had a really difficult time with bringing all this data together. They're traditionally brick and mortar, and now they have this huge online sales channel, all the data coming in on a separate platform. And so they're asking, how do we bring this data together so our business users can ask business questions of everything in inventory from brick and mortar all the way to the online sales channel. And so what they had stood up, this is before APS was even in the picture, they had their Hadoop system and they were using what's called Scoop. So again, if you're familiar with Hadoop, in the Hadoop ecosystem, there is a tool called Scoop. And Scoop is essentially the tool that's used to take all of the data from Hadoop and stream it, load it to a relational database. And within the Hadoop ecosystem, Scoop is pretty much the fastest way you're going to get data out of a Hadoop system into a relational database. And what we were seeing is with this method of access over 10 gigabit per line, the customer is taking 10 hours to transfer all of that data out from Hadoop. This is the data that their business users need to actually run reports, do analytics. So if you think about that, 10 hours is a long time. You kind of hard get in that batch window, overnight in that 10 hours, right? Because there's a bunch of other stuff you have to do. I'm just telling you the first step here. That's extracting the data. We haven't even done transform loads, all that good stuff, ETL. So the customer was transferring that data out 10 hours, and they were transferring into a SQL Server system with Scoop. And once they got into the SQL Server system, this was a lot of data, so they couldn't just give all this data up to their business users, right? They were exposing the data to dashboards and reports using analysis services, and they had Cube and analysis services, but before they could actually have analysis services up to SQL Server and bring that Cube in, they had to aggregate the data. So it was just too big until they could bring it into the Cube. So you have an aggregation process that happens on the SQL Server instance. This was taking the customer 3 hours. So next we have the process for analysis services, right? You do the aggregation in SQL Server, you have your data set now that can be consumed by the Cube, and you have analysis services, it's going to build a MOLAP Cube. And can anyone tell me what happens when you build a MOLAP Cube? What does analysis service do to SQL Server? Very simple, right? It sucks in data, right? You're building a MOLAP Cube, and a MOLAP Cube means you're actually building a physical structure in analysis services, a cube. And so SSAS has to suck in all that data from SQL Server and build a cube. And so this was taking the customer 1 hour to build the cube, and then expose it for dashboard and report. So a total end-to-end time of 14 hours to deliver data to the business. And this was just too long, right? They're not going to be able to 6 a.m. have the data exposed for them to actually do reports. So the customer came to us and said, hey, listen, we're having a really tough time. It's not only big data that's giving us trouble, it's this regular database stuff. We have a ton of data, we're trying to aggregate it, it takes a long time to build a cube. And so they looked at APS to try to solve this solution problem. And so we look back at that big data architecture, and we look at it after in terms of where do we actually place APS. And remember I told you, APS is like almost a cousin of SQL Server, right? They come from the same code branch, they're both relational databases, but one's made purpose-built for data warehousing and analytics. And so when we brought the APS system in, we were able to use Polybase. And we'll talk about this more, but really Polybase is this powerful ingestion mechanism that can bring the data much faster than any other tool that we have in the Hadoop ecosystem. So we use Polybase, we extract the data out of Hadoop, we turn that 10-hour time frame to 1.5 hours. So again, this is the fastest way I've ever seen you're going to get Hadoop data to a relational database. We then took that data, and instead of having a 3-hour aggregation time on this APS platform, we did it in 30 minutes. And then if you look over at analysis analysis services, you're going to see that the queue build only took us 2 minutes. Now, can anyone tell me why this queue build only took 2 minutes now if it's the same data set? The answer's on there. It's rollout, right? And so, yeah, I mean, rollout, that's been around for a really long time. It's nothing that cool, right? But the problem with rollout is that we haven't had a back-end database that's powerful enough to really service rollout type queries, right? Because with rollout, we're not actually building a queue. We're just building the metadata for that queue analysis services. And then all the queries that come down to that queue analysis services is actually getting serviced by the back-end database. In this case, it's APS. And so you see, not only did we take this 14-hour data process down to 2 hours, but we actually bought a lot more for the customer, right? Because now we have the ability in this short time frame to refresh the data much more quickly. Right? With a 14-hour time frame getting the data to the business, I can only do that once a day. I can't even do that twice a day. It's not that many hours in a day, right? But now that I'm doing it every 2 hours, I have the ability to say, 1 p.m. I'm going to refresh the data, right? 3 p.m. I'm going to refresh the data. You now have this ability to get the more real-time, lower latency data to your business users. And because this is rollout, you actually are going against the fresh data. You're going back to the back-end database, and you do have the ability to do things like real time.
Can we go to details on the previous screen a bit? What is polybase?
I'm going to teach you that. We'll get to it.
And when you're going to describe the data, can you get into details what size of the data you're talking about?
I'll show you the size of this data. This was, and I'm going to back into it. I know that the customer was using Scoop, the fastest mechanism, the fastest throughput they could get from Scoop, and they tried many different ways. Specifically, gigabits, 50 gigabytes per hour. So that's 500 gigs, it's half a terabyte that they were doing. And we got whatever the math is for 1.5 hours of transfer sync data.
Do you have any metrics on the query performance differences between the rollout queue and the rollout queue?
I don't have any that I can share with you, but it's a very good question. There were some queries that were slower actually with the rollout queue. And what you see is in terms of the data access patterns, so if there are more dashboards, little or quick lookups, it's a toss-up between which system's faster. And this is actually, that's a great question. This is very key in that I would never position this APS platform for any type of transactional processing, any type of OLTP, because when it comes to looking up small pieces of data, this is just as fast or slower than SQL Server. Right? Actually, SQL Server has in-memory and it has some very special things to make transactional processing very, very fast. APS doesn't make transactional processing fast at all. But if you come to me and say, hey, I have this query on SQL Server that's taking 40 minutes or 2 hours, and it's going after millions or billions of records, this system will do it in seconds. And so it's a little bit of the difference of how we architected the system internally, specifically for data warehousing analytics. Great question, thank you. So let's talk a little bit, you got the use case, you got the data warehouse challenges, you understand why would Microsoft even create this platform in the first place. So now I want to talk a little bit about the value proposition, each of those technologies within the APS appliance, and really what it delivers for our customers. So when we talk about PDW, the relational platform in the appliance, this is really our high-performance engine. This is where customers come into the PDW system because they want to exceed their ETL SLAs. They want to move from the 6 a.m. time frame to loading data every couple of hours or every 5 minutes. Actually, I have one customer with very low latency. Taking queries down from hours to seconds, completely removing the need to build queues, removing the need to aggregate data, greatly reducing the administration and cost. So what you'll see in the appliance platform is we've built a lot of the best practices in. There's actually things we're not going to allow you to do, intentionally not allow you to do, because we've automated some of these processes for big data, for data warehousing. The next area is Polybase. Again, I'll keep hitting on this is the flagship technology. A lot of our research and development went into creating Polybase. We feel it's a big differentiator for us in terms of what we're doing. And what Polybase really is the bold claim here. It's federated queries at scale. It can Can anyone tell me what a federated query is?
Set up like XML messages to the first database. And
Yes.
XML return messages that are currently multi-threaded.
Absolutely, great. So, taking that up to a higher level, a federated query is basically a query that is getting sent out to separate systems, right? It's a query that's saying, I have some data in this system over here, and I have some data in this system over here. I'm going to write a single query, and there's some machine or computer or whatever that's going to take that query and spread it out to different systems, combine the data, and bring it back to me. And so, federated query technology has been around for a long time. This is not something new. We didn't invent federated query technology, but the key to what we're talking about here is that it's federated queries at scale. And so traditionally, if you think about federated query technology, it's been very difficult to do at scale because you're going out to these separate systems, and if those systems have a lot of data and you're pulling it all back to a central location, what becomes your bottleneck? Your network becomes a bottleneck, right? Because you have to move all this data, all as it is, and bring it to a single place and then process your query. And so we're actually doing some very intelligent things to surpass this bottleneck in terms of federated query technologies. The first thing that we're doing is we're doing parallel push and pull of data. And so what you'll see as I go into the PDW architecture at MPP, if you're familiar with massive parallel processing, it's multiple physical nodes chained up together. And so when I say parallel processing, I have these multiple physical nodes that in parallel are all talking to each other and sending data back and forth. And so why does this scale? This scales because if I start with a system with 2 nodes, and I'm pushing and pulling data in parallel, and now I have a system with 4 nodes, and I'm pushing data in parallel, I've just doubled my throughput. And so as these systems scale, the performance of your query scales with it in terms of data transfer. Now, data transfer is only one piece of the federated query solution. The second piece of the federated query solution is push-down computation. And what push-down computation means is, I'm going to take this query, I'm going to understand this query, and I'm going to take portions of it where the data is, if it's in the cloud or if it's in Hadoop, and I'm actually going to process parts of the query where the data is. So I'm not going to write a query that brings all this data back and then processes the query. I'm going to push the query out to where the data is on those platforms, and I'm going to process that query where the data is. In this case, it's Hadoop specific. The next thing we're doing is cost-based split query processing, and that's a tongue twister, which is basically saying we're looking at the cost of this. It's not always beneficial for us to push down computation to a Hadoop cluster. If you guys are familiar with Hadoop, there's this programming framework that's called MapReduce. And it's basically Java, it's running Java in a parallel framework. And it takes about 20 or 30 seconds to actually spin up a MapReduce job, depending on the distribution of Hadoop that you're using. But if I have a business user that's running the query, and it's a short query, they're only looking up little portions of data, they don't want to wait 20 or 30 seconds for a job to spin. And so we're actually looking at what is the query asking for? Is the query only asking for a couple of megabytes of data? Just suck all that data in. You don't even need to push down a MapReduce job. So cost-based split query processing. The beauty of all this is the T-SQL interface, and what I'll show you later is you're going to have business users on the platform writing queries. They don't even know the data's in Hadoop. They're just writing regular queries. And finally, we'll talk about data schema virtualization, where we just put metadata of the structure of Hadoop files in SQL Server. So we don't actually bind at the time of the table creation. I'll show you what that means a little bit later. And the final area in terms of the value proposition is Hadoop. And I'll take a little bit of time here now. We talked about within the APS appliance here, you have this box. Within the appliance, you have the option. You don't have to take it, but you have the option of adding HD Insight. Now, HD Insight is the distribution of Hadoop from Windows, from Microsoft. It's in partnership with Hortonworks. That's one of the leading distributions of Hadoop today. And you do have that option. And really, the recommendation here is if you haven't started on Hadoop, you don't really want to get too big on Hadoop. You want the platform, but you want to ease in terms of growing into it. We think that HD Insight is a really good option for our customers because, as Microsoft does, we make it easier, we make it more productive in terms of your usage. But we wanted to make sure that we integrate with the ecosystem of the new tools. And so what you'll see is that many times I'll even recommend that you go with what already works on Linux, right? Depending on what you're trying to do, we have options in terms of what type of Hadoop that you actually connect to the system. And we support those different distributions of Hadoop. It could be Cloudera on Linux, it could be Hortonworks on Linux, it could be Hortonworks on Windows. We support those evenly. So we don't make a distinction between one or the other, and that's intentional. Okay. So before we go any further, I gotta allow you guys a little bit of some of the demo and performance of the system. So as we promised, I do have access to a demo appliance. Now, you don't know about the architecture yet, and so this will help you understand more as we go further, but I'll just tell you now that the system that I'm running on is an 8-node appliance. And you can think of nodes as horsepower. So if I tell you 2-node appliance, that's only 1/4 the power of an 8-node appliance. Or an 8-node appliance is 4 times more powerful than a 2-node appliance. Okay? And I say this because this may be a little bit too fast for you, but the reason I say is you have options in terms of how you grow out this system. So this is an 8-node, but you can start off, our smallest footprint is a 2-node. And so what you'll see here is I'm connected via SQL Server Data Tools. This is just a client machine I'm connected to. And this system is connected up to the PDW appliance with 8 nodes under the covers. And you'll see here that I'm just going to do some simple queries. I'm going to ask you guys to validate. So we just have a count star here on the fact sales table. And can you guys tell me how many rows you see there? A lot, I keep being honest. I know there's no columns, I should have had it honest. Well, I'll tell you if you guys believe me. It's 1 billion rows. Okay? And if you didn't see it, I'm gonna do this one more time. Now look where this number is because I'm clicking this really fast. Okay, so under a second in terms of doing a count star on a billion row table now, I know, count star isn't really that sexy. It's a simple query, right? When count star. How many business users come and say they have a problem with count star? Just a select count star, nothing else. But what you're starting to see is that even the most simplest things at a small level are very, very fast on the platform when we go after large amounts of data. So let's take that further, let's keep on going. And we take that billion row fact sales table and we say, okay, we want to join into the date dimension. We want to basically see what our sales were per calendar year. It's a simple query. And you see here, I have no where criteria. It's going over that full data set. It's from 2006 to 2011. And you see here, it's all the rows across that billion row table. Again, I'll run it one more time, but you'll see it's coming back in that sub-second time frame, milliseconds in terms of speed. No, we'll get progressively worse and worse in terms of the queries that run against this thing. Now, the next question you might ask, well, these count stars, you can get smart in the database and figure out how I can optimize a count star. I can look at the data blocks and estimate the number of rows, or I can keep it count internally. So yeah, count star we can optimize in a lot of ways. Now, if you look at this next query here, next query you're going to see is this is just a select min and max from a column. And so you can come back and you say, well, Sean, you created an index on that one column. You're going to do select min and max, and it's only going to scan that table, and so you have a lot of data blocks or I/O operations you don't have to do, and you're correct. But remember, I went back to that fact that the way we architect this platform is speed inherently, and so we don't want our users coming in, or DBAs or IT, and basically trying to figure out what questions the business is going to ask of the data. So I'm showing you the DDL of this table specifically because I want you to see that there is no specific indexes on that column. In fact, we're using cluster column store index, if you're familiar with that. And that gives us a lot of our power, but it's the power of the distributions of the parallel processing that actually gets us this billion row tables in a second. So just proving to you guys that there isn't any special columns on this, on any special indexes on this column. And I'm going to go ahead and run that. And certainly, yeah, this one takes longer, right? But it doesn't take that long. It takes 3 seconds. I want to be clear here. When I'm running this min and max on this column, I literally have to look at every single data block for this column, right? I have to literally see every value to find out what the min and max is. And this is doing that in that 3 seconds on that billion row table. couple more for you as we get a little bit more complex in terms of the query. So now we're saying, let's take this billion-row fact sales table, let's join it with a customer dimension, a geography, date dimension. We're going to do multiple group by's, we're going to do multiple aggregations here. And this is a typical query for any company that's basically trying to find out what their sales amount, cost, and profit were. And again, you'll see there's no criteria. There's that billion-row fact sales table. So we're going against the full data set. And it's back. So you guys impressed? Is this fast? Yeah?
And the SQL Server 2014, right?
This is 2012, but don't get caught on the version because this is PDW, right? And so we take the master branch of the SQL Server code base and then we make PDW for it. So I'll give you guys a great example. We were on SQL 2012, our main code base, a couple years ago when we introduced clustered column store index. So if you were an APS or a PDW customer year back, you had this clustered column store index technology before SQL Server ever had it, before it was in SQL 2014. And so what you're actually going to see with Microsoft's engineering groups is they kind of take back and forth from each other. So our next release, which is coming out in a couple of months, it's on SQL 2014, and we're taking that and making more optimizations to it. But it's not equivalent in terms of the version of SQL Server. It's just whatever code branch that we use to build off.
Well, in this example, if you have 2012, you actually build column store index, you cannot insert anything, right? You're just reading.
So let's be clear. This is PDW. It's not SQL 2012. And it has a cluster column store index, which you can load. We can figure out the details of that later. Okay, one more query, and then we're going to get back to presentation, guys. Don't worry, I'll have much more demo for you. We're very good stuff happening. So again, this is one more call an ASCII query. It's really not on the APS system, but here we're doing again against that. I thought it was against the building row. It was against 2009. And you have ranking, partition. You have multiple joins. You have group by subqueries, etc. So again, that's coming back in a couple seconds now. One other thing I wanted to show you. This wasn't enough, and I'll come back for more. Is 5 building rows. I got to do count date here because I actually have an arithmetic overflow. Okay, you'll see 5 billion under a second, right? And don't worry, I'm going to explain to you how it's actually doing it under the covers so you understand how we're getting this performance. Stick with it. Okay. So this next section, I'm going to hit those 5 data warehouse challenges. If you look here, you see all the ones that I talked about, the volumes, the BI analytics, the big data design in the cloud. I'll be brief here. These are a little bit more on the marketing side, just talking about the value proposition. I don't want to spend too much time on this. I'm going to move on from this and go over to the technical part, okay? Spend a little bit of time here. Okay, so let's take a look at volumes. And this is one of the concepts I alluded to earlier in terms of describing an APS appliance in that it's modular, okay? And so what you're looking at here is basically how you grow out an APS appliance. Now you'll notice that there's that box, and I'll keep referring to this box. And I want to be very clear with you guys. There is no decoupling of the hardware and software, okay? And there's pros and there's cons to this, and we can sit in debate of all the goods and all the bads, right? With any technology decision, there's goods and bads. But we feel there's a lot more goods in terms of building it in terms of hardware, software, appliance than there are bads. And we'll explain why that is specifically. But keep that in mind. If you purchase APS appliance, it's married together, hardware, software. You're not going to take our bits and install it on your own servers. Okay? Now, if you do choose to purchase the APS appliance, you have options in terms of how you purchase it and how you grow. So if we start off with this box all the way here on the left, you'll see that this smaller box here in darker gray PDW is what we call our entry-level footprint. And so if you come in and say, Sean, we have a lot of data warehouse challenges, but we want to kind of ease into growing and meeting those challenges, then you can start off with that entry-level footprint. And that entry-level footprint is going to be a quarter of a rack from HP. So we take a rack, a cabinet of hardware, and we fill it up with a quarter of the weights in terms of servers, storage, and networking. So So that box has everything you need inside of it in terms of running your data warehouse. There's no more reliance on SAN. It's dedicated direct attached storage, and it's an internal dedicated network. It's actually running 56 gigabit InfiniBand. And so you start off with that single scale unit of PDW, and now as you grow, you have the option in terms of saying, hey Sean, we have a lot more data coming in, we have a lot of applications, we're running out of gas on PDW, we need more horsepower, we need more data space. And so if you think about traditional in the database world, you know, I talked to some of my customers, they had the same challenge with their data warehouse area on SQL 2012, and they said, well, I can take what I have now and then we'll start prototyping on 2014 and I'll re-architect and I'll figure out, you know, all the new features in 2014 and we'll get a lot more performance out of it. And they did. Typically it's on, you know, the 40%, 50%. It's not orders of magnitude in terms of performance unless you're doing in-memory OLTP. But for data warehousing, it's usually in the 30 or 40% range from what I saw. And what we have here is dramatically different in terms of increasing your performance. So there is no ripping and replacing of your environment. There's no forcing you to upgrade to the latest version. When you come to us and say, hey Sean, we need more power in PDW, you add another one of these scale units of PDW. When you add another one of those scale units of PDW, you're adding double the servers, double the storage, and the networking's fast enough to support all of that. And what does this do? This distributes your data across the platform, and actually your queries are running twice as fast. Your ETL loads are running twice as fast. Caveat, this is a full table type operation, so you're not looking up a row or reading a row, right? That whole keeping for data warehouse. You also have the option to say, Sean, we have PDW, we're getting a lot of demand from our business, it's a big data thing, we want to bring in Hadoop, we want to connect it to our data warehouse. And so within that same APS appliance, you now have the option of saying, we have our PDW, but we want to add Hadoop. And so you can keep adding these scale units in until you add 4 of them to a single cabinet. Once you fill up that single cabinet, you say, Sean, that's not enough, I need more. We'll add another cabinet next to that, and we'll keep going. So today we support up to 6 petabytes. If you guys have a problem, to hear the 6 petabytes, come talk to me afterwards, and we'll get engineering involved. The next area, and I keep alluding to this, basically we've taken SQL Server, it's massively parallel processing. We'll go into detail on how that works technically, and you'll get an understanding of how we're getting all that performance. But I want to be clear in the differences between SQL Server and PDW in that we took the SQL Server code base and created it for a massively parallel processing system. And we've converted a lot of the code in SQL Server to do that, but not everything. So there's certain functions that we turned off intentionally and we'll probably never turn on. And there's some functions that are non-trivial in terms of turning on SQL Server. If I take them and I put in a parallel architecture, it's not easy for me to actually make that run faster. There's a lot of thought put into how do you make that run faster in a parallel environment. And so, to give you an example, cursors are not in the APS platform, and they'll probably never be. It's not on our roadmap. Engineering doesn't care about cursors, and they don't really want to have cursors running on the platform. Can anyone tell me why? Performance, right? They don't want to use cursors for the performance, and that's because cursors are running at they're not using set-based theory in terms of their processing, right? It's a row at a time processing. For example, if you think about some of the more difficult ones, it's like UDFs we haven't turned on, for example, because those are the non-trivial types of functionality to put in an appliance to actually run a lot faster. And we do have a migration guide if you go to microsoft.com/APS. Detailed white paper, things like 60 pages, so it tells you everything you need to know about the differences between the two platforms. We're using in-memory columnar. That's great. You guys know about that. So we talked about Polybase. Again, this is more the marketing stuff, so I'm going to skip through this. I want to actually get into more of the technical parts. Now, one of the things that I mentioned was around the hardware-software appliance. We do differentiate ourselves in that we give our customers options in terms of what hardware you actually run the appliance on. So, though you do have to purchase a specific configuration of the hardware, you're not purchasing that hardware from Microsoft, you're purchasing it from HP, Dell, or Quanta. You have the option of which vendor you choose. And in fact, these servers are your standard servers from this vendor. So for HP, we're using DL360s. For Dell, we're using R620s. Okay. I'm sure you guys, if you use HP or Dell, you probably have those servers in your data center today. Some of the other areas we're using Windows storage spaces, Hyper-V virtualization. We build this system as mission critical. So within that box in the appliance, if any component goes down, the server goes down, storage goes down, networking goes down, everything is fully redundant and the system is still online. The other area, and this is, I was talking about the pros and cons of hardware versus software. And I'll give you the con that I have a customer tell me, said, well, I just bought this beefy HP DL980, right? I don't want to go buy their hardware for this platform. I just spent all this money on the DL980. So certainly there are the pros and cons in terms of when you're deciding to make this purchase, but these are all the pros in terms of what we see versus our customers trying to stand up their own environment. And I'll call out what I think is the biggest one, which is SAN. And so even if you have your SAN architected in a very powerful way, and you know exactly what it's doing, a lot of times what we start to see is the SAN controller becomes a bottleneck for SAN-intensive workloads. What we've done is we're actually using direct attached storage to each one of our servers in parallel. And so from an I/O bandwidth perspective, it's unmatched against the SAN. Okay? And so that's one of the key areas in terms of where we get the performance from. A lot of times as you start to grow out these environments, and I talk about the cost, you'll see that the SAN cost actually gets pretty dramatic as you grow out these environments. And finally, cloud. What you'll see today and everything I talk about with Polybase, in terms of writing a query against data in Hadoop, you can do in the cloud. So if you're familiar with Azure storage, there's Azure Blob Storage. You can actually store data in Azure Blob Storage, and then write a regular query against a normal table here in PW, and it will actually access data in Azure Cloud. But I want to be clear that we don't have that push-down computation yet. Okay? So that's one of the key things that our customers are asking for, because you don't want to be moving too much data back and forth from the cloud. So that's one of the areas that we're working on. But when it comes to disaster recovery, in terms of keeping your data online for historical purposes, keeping it up in Azure to do geo-redundancy, disaster recovery, high availability, it delivers a lot of value for our customers. Okay. Done with jumping around. Any questions on anything I covered there? Everybody with me? I'm going to actually do one more demo for you guys. Be even more strenuous than the last one. So you remember we did that counter on the 5 billion row table, right? You guys see 5 billion there? Permanent? So me and some of our peers, we said, okay, let's write a big, really big query that's going to take time on the system. So we took that 5 billion rows, and we said, okay, we're going to write a query here where we're going to do some left outer joins. With each one of these subqueries, we have ranking, partition, aggregations, multiple joins. And keep in mind, this is all against that 5 billion row fact sales table. We have group bys in here as well. And then we do another left outer join against that 5 billion row fact sales table. And then we do another left outer join, that 5 billion row fact sales table. So how long do you guys think this query is going to take? And what you've seen, empirical evidence you've seen so far? 5 seconds? Yeah, that's good, yeah. Good. Let's see. I gotta be careful with that question. Tell me 1 second. Can't really 1 second. Maybe with the double the nose. 8 seconds. Okay? So this is 3 left outer joins, subqueries, 5 billion row table, multiple inner joins within there, group bys, ranking. I mean, the kitchen sink, right? We're throwing everything at this query as much as we could at least. Now, certainly, if you write a Cartesian product join against 2 5 billion row tables, that would probably take a long time for the turn, right? But you're starting to see, for relevant queries, for real queries that business users are actually writing against this data, this system performs dramatically better than any data warehouse technology that you've seen. Okay. So that's a little intermission demo. Hopefully, some of the technical stuff will be more exciting for you guys in terms of understanding how this works. And yeah, I mean, we can take questions if it's too deep of a question, maybe wait for afterwards, but if it's something I talk about.
I'm just, and maybe you guys have improved your performance. I'm curious, on the previous 2-3 demonstrations, on the bottom right, it says returning 300 rows.
Yep.
I'm curious as to what you're showing there in terms of the selectivity, the distribution of the data, you mentioned that the set of operations, which is cool, which is how it should be done. But is it really returning the entire set of the full ways and cache, and why? I've seen 2 out of your 3 is 300 rows. That's kind of, and also after that, and you don't have to address that, and then also on how you would get more standard benchmarking. You guys have done it, but I've not seen the actual unpublished H queries benchmarks.
Yeah, so I'll take the benchmarking offline, because that's actually a very interesting question in this space. We can talk about that. In regards to the 300 rows, I don't really see that as an issue, because I'm not, and keep in mind, I'm not testing how fast I can transfer rows from the database to the client machine. I'm testing how fast the database can process the query and generate a result set. So for me, it'd be equivalent even if I put a select count star around this, right? Because it actually first has to do all the processing internally to understand what the count star is for the valid rows inside of it, okay? So the reason why I'm not returning 10,000 rows or 1,000,000 rows or 2,000,000 rows is because as I increase the number of result sets that need to be returned to the client machine, we're starting to measure the actual time it takes to do data transfer over the network, which, if I'm looking at a 1-second query, can actually affect the performance of it, right?
I have a quick question.
Sure.
So you talked about Azure and the cloud, and there's Hadoop and Polybase and whatnot, and you're running these queries. Where exactly is this data sitting?
Sure. All of the queries that I'm running right now is within the PW appliance. And so as I go further in the demo, I'll start to show you queries where we use Polybase, where I do have a Hadoop cluster outside of the appliance that I'm reaching into. And you'll see that when, actually, I'll show you when I'm doing like 2,000,000 rows, it's dramatically slower, because you actually have to have that data pulled in from a separate system.
Will you be,
Okay, one more question. Sorry, the hanging.
yeah, that beginner, that small footprint system, how much storage is it?
The small footprint system, 2 nodes, it comes with 15 terabytes of storage for your data. So that's after we've already taken into account database overhead and all of that. That's 15 terabytes uncompressed. So if you remember back when I said best practices in appliance, everything is compressed automatically. And so what we see in practice is, I'd say 90% of the tables that my customers store in the appliance are columnar. And even at a low end, you get about 5x compression. So I mean, that's a really good point, because that 2-node system can store 70 terabytes of data, of your data. And we have the option to go with 2 terabyte hard drives or 3 terabyte hard drives to make it double or triple that number. And it's a really good question, because I never ever have a customer upgrading their appliance because they're running out of data. And there's a physical reason for why that is, because when we're building the appliance, and we're figuring out for each one of these servers with direct attached storage, how many hard disk drives should we place behind that server? We're not determining how many hard disk drives we're going to place behind that server because we're saying, hey, we want to have 15 terabytes behind that server. We're placing the number of hard disk drives behind that server because each one of those hard disk drives has a certain transfer speed. And so we want to deliver the I/O bandwidth. And so as a result of that, if you think about a hard disk drive, the speed of the data coming out of a regular hard disk drive stays pretty much the same, unless it's 72 RPM getting faster, but the actual data capacity is grown, right? If you look at a 500 gig drive versus a terabyte drive, they're the same price point depending on a year or two back, right? And so that's really why it works out that way. Okay. So hopefully now we're going to go over the logical architecture of PDW, and this is everything's going to become clear. You're going to understand, well, now I know how it's actually processing so fast. And when we start off with the PDW logical architecture, we first start off with the control server, and this is also known as the brains. And the reason it's called the brains is because this is where all the smarts happen. This is where we actually take in a query into the appliance. We say, what does this query look like? How do we make it into a parallel query to run across our system? The second type of server that we have within the PDW logical architecture is the compute server, what you guys here in calling nodes for short. And the compute server is known as the brawn of the operation. And as you can imagine, it's called the brawn because this is where the actual query processing takes place. You'll also notice that there isn't just one compute server, there's multiple compute servers. So when I talk about 2 nodes or 8 nodes, I'm referring to those compute nodes because those are where the actual horsepower is. The control server, the brains, that always stays the same. But as we grow out this environment, we want to grow out the compute nodes for the actual brawn, query processing. You'll also notice that each one of those compute servers has direct attached storage as we've designated in the diagram. So that's where we're really getting the power of the system is we have this I/O bandwidth that can't really be matched by any other data warehouse product. Now when a user comes in, there's a set of steps that occur to actually process a query. When a user comes in, they'll log into the control server. It's like a regular SQL Server instance. They have their username and password or integrated authentication. They write a regular query against regular tables. They don't know about all this control server, compute server stuff. Okay, it's a regular database for them. But when they actually log into the PDW appliance, they're going to connect into the control server and they're going to submit their query to the control server. And the control server, it's called the brains really because that's where the optimizer lives, the parallel aware optimizer. And it takes in a query and it says, how do I take this query and break this query out into smaller, separate queries and have them all run simultaneously in parallel. And so the control server will take this single query, and keeping the example simple, it will break this single query into 3 smaller queries, and it will have each one of those smaller queries run on each compute server in parallel. Now also keep in mind that the data for your tables is spread across these compute servers, so that each of these queries running on its own compute server can get satisfied by the data that's there. There's also certain features and functionalities within each one of these servers that's actually allowing this processing to occur. So from the control server perspective, you have the optimizer, the metadata, the statistics, and you have what we call our proverbial secret sauce. This is the data movement services. Again, this is probably the second area where we spend most of our R&D. And the reason for that is, listen, when you're talking about a relational system in a parallel environment, and you have users writing these relational queries, what are they doing? They're joining up data together, right? And if you're joining up the data together in a parallel environment, you have to move data. Okay? No one's figured it out. They'll make billions of dollars if they figure out how they can process a query in a parallel environment without actually moving it into data. Okay? And so what we've done is we said, we want to build into the parallel query optimizer the most efficient way to move data around this platform. So you'll see that data movement services lives on the control server to facilitate that, but we also have data movement services running across the appliance on each one of the compute servers to facilitate that as well. And finally, we have here the table distribution and geometry, which I will discuss in the next slide. So let's talk about the data distribution and how that works. And here you have a regular fact sales table. You have all the typical things that you'll see in your DDL. You have your column names and your data types. What you have in SQL Server, clustered index, partitioning, etc. You'll notice something's missing down here. Anybody want to call that out? What you'll notice is missing is the on keyword. Remember? So I told you that data placement is automatic. We've completely removed the on keyword. And this is intentional because we don't want our DBAs focusing on where to actually place data on this platform. We want our DBAs focusing on bringing new data into the platform, exposing more data for analytics, right? More high value areas for the business, because what we're starting to see is IT can't keep up with all the demand from the business when it comes to information management, right? So we're automating some of this low-level stuff, and no one really cares, and we're exposing some of the higher-level stuff in terms of query performance, analytics, being able to load the data very fast. Now, that's something that we've removed, but we've added something, right? So I didn't say everything is free. There is a little bit of a learning curve. You have to learn how to work in a parallel environment. And really the key that you're going to see for working in a parallel environment is this concept of distribution. It's not the same thing as partitioning. When I talk about distribution, I'm talking about how do I take a regular table and distribute that table across multiple physical servers. That's what we're talking about with distribution. And the way the APS appliance facilitates distribution is through a logical construct. And so you see here that logical construct is just one of the columns in your table. And I'm using big words, maybe it's a little bit complex, logical constructs and all that, but it's actually quite intuitive. So if you look here, and I'm going to give you an example of the table, let's say that we have the customer dimension, right? Everybody's used to the customer table, customer dimension. And you have someone come in and they've never worked with APS, they want to get things done fast, so they say, hey Sean, I got to create this customer dimension on the APS appliance, and I'm looking at the help file and it says something about a distribution key, I got to choose one of the columns in this table. So Sean, I'm looking at this customer table and I think I'm going to choose gender as my distribution key. So you guys tell me if you think gender is a good distribution key for a customer table? No. Why is gender not a good distribution key? There's only two values, right? Right. So see, you guys already intuitively understand the concept of distribution. And the first concept of distribution is you want to get good distribution. And you can't get good distribution if you're using values that have a low cardinality. And so the first thing you want to think about, it doesn't have to be unique, you don't have to have a unique column. You want to choose one of the columns in your table that has a high cardinality that'll get you good distribution. So you wouldn't choose gender, you would choose customer ID, or one of the values that gets you that good distribution, okay? Here you see that we use product key.
Could you get combination?
What's that?
Could you get the combination of keys?
We use compound columns to do that.
Compound, okay.
Yeah. Okay, so you guys got the logical architecture down, right? That's good? All right. I'm going to test it. So I'm going to go through a couple of math questions here. There's no trick questions, so just feel free to answer, okay? Don't be shy. So we have our logical architecture here again, control nodes and compute nodes, and we come in and say we want to create this fact sales table. The user comes into the system, they log in with their username and password, they submit table creation to the control node. Then the control node says, okay, I'm going to create metadata about this table. I don't actually store the data for this table on the control node, but I want to know it exists, I want to know what it looks like. And then the next step that happens says, well, the control node wants to create this table on all those compute nodes down there. And for the control node to create all these tables on the compute nodes, it has to send down and create table statement. And so to that math problem I was talking about, let's just say, for example, that I had 1 compute node, 2 compute node, 3, 4, 5, 6, 7, 8, 9, 10. So I have a total of 10 compute nodes. And now I have this control node saying, hey, I want to create the fact sales table on all of these 10 compute nodes. So how many create table statements would the control node have to send down to create this table across all the compute nodes? Anyone tell me? 1? 10. That's right. Because there's 10 compute nodes, they're separate, and so I want to create the table on each one of them, so the control node is going to send down 10 separate statements. That's what you would intuitively think. But that's not actually correct in terms of how we're doing it. When we create this table on our system with 10 compute nodes, we're not actually creating 10 fact sales tables, we're creating 80. We're creating 80. Okay? And so what's actually happening is instead of creating one distribution of this fact sales table per compute node, I'm creating 8 distributions per compute node. Why? Because not only can I get parallelism across physical nodes, But hey, this computer thing is multi-threaded and parallel inside of it too, isn't it?
Yeah.
So I can get parallelism inside of each one of those nodes. And so remember I went back to, here's one of the pros of the hardware and software married together, is these are Intel dual socket 8-core chips, 16 HDDs in array 1 configuration. And so each one of these distributions literally has its own dedicated I/O bandwidth and CPU in terms of processing its query. This is parallel processing, share nothing, right? I got my own disk, I got my own CPU thread or core inside of that CPU, and I'm processing my portion of the query and I don't have to worry about anyone else. And why don't I want to worry about anyone else? Because think if we all just went and tried to go out that door, right? There'd be a coordination issue. Right? And if you're actually having to talk to all these other compute nodes to satisfy your own query, you start to get a lot of noise in terms of the efficiency of processing the query. So we do this in a shared nothing architecture, and we are creating 80 tables for this one back sales table. But I want to be very clear. The user, the business user, your tools, they have no idea any of this is happening. Okay? From a user perspective, from a tool perspective, it's SQL Server, they log in, they write a regular query against a regular table. You saw those queries I was running in the demo? Each one of those queries is running against 80 distributions of each one of those tables under the covers. Okay? That's where the power comes from the system. It's in this distribution and parallel processing of the data. Yes?
Hadoop has redundancy, right?
Yes.
All problems. Are these tables gonna confuse, have redundancies?
So Hadoop is using data replication. We're using RAID 1 mirroring. So we do have redundancy. If data goes down, the data is still online. We have the same thing, but we use a different architecture to actually get that.
You mirror in the different nodes?
We mirror the disk layer. So every disk has a pair, and the data on
On
that
one
disk.
node? On the same
All the
node?
nodes, yeah, on the same node, yes.
On the same node, not different.
Not different nodes.
Okay,
Um,
so
and-
that node will not create redundant tables.
It doesn't create redundant tables. Under the covers in that hardware architecture, we're doing data redundancy at the disk level.
So what happens if a node fails?
That's a great question, and I have a slide. There's a couple of high availability questions you guys can give me. So I'll tell you, and then if you guys want more, maybe after the session, I'll show you. I can break every component and show you how the system is still online. If a node goes down within that cabinet, we have a failover node, which I didn't show you the architecture. If one of the nodes goes down, we're using Hyper-V virtualization. That virtual instance automatically migrates over to a failover, and the system is online. So again, if any component goes down, the network goes down, a disk goes down, disk enclosure goes down, server goes down, the system is still online. It's fully redundant, mission-critical system.
Each node has a unique data set, or they just identical?
Both. And I'll tell you guys why. I'm going to get to that in a second. I'll show you that in a second. One other point that I wanted to mention here, guys, is I said the user has no idea this is happening, right? They just run their query and it runs. Under the covers, you have these 80 distributions, and what's actually happening when I submit one query to this system, it's actually running 80 queries, each on 1/80th of the data. Okay? That's what these distributions are doing. One query turns into 80 queries. Each one of those queries is on 1/80th of the data.
That's assuming a 10-node box, right?
That's assuming a 10-node box. Exactly. And for a 2-node, it would be 16. It would be 16 queries on 1/16th of the data, because each node has 8 distributions, or 8 parallel processing mechanisms.
It again depends on your CPU numbers, right? It can be each node has 16.
We architected it so that we can take advantage of the hardware, yes. Yeah. And so, great point that as we go to the next generations, we might add more distributions per node, depending on what CPU class we go to. Last thing I want to mention here is distribution, and this is to your point, sir, about is the data replicated or is it unique in terms of the nodes. For this table here, where I say distribution equals hash, the data is unique across the distributions. And to give you an example of this, let's say very simply that this fact sales table had 160 rows, 160 rows. and I loaded this table, or all of these 160 rows, I loaded it to APS, and I loaded it to these 80 distributions. So if I had 160 rows and they spread evenly across these 80 distributions, how many rows would I have per distribution? 2, that's right. So in this case, where the table says distribution equals hash, the data is unique. And so I actually take the rows of the data, I hash each row, and I say one row goes here, one row goes here, one row goes here, spread. And the reason I told you both is because we looked at this and we said, when we looked at the query patterns for our customers, we said, we know there's a lot of these tables that are really big, your back sales table, and we can't replicate those because they're really big. But we also saw a lot of our customers have these small tables, right? They have a dimension table, they have a lookup table, and their queries are constantly joining to these tables, big table to the smaller tables. And so we do give you the option to say distribution equals replicate. And when we say distribution equals replicate, we're going to take this whole entire table and we're going to copy the whole table across every single distribution. And some people, oh my God, you're duplicating data. You're not allowed to do that. But you know what? For these smaller tables, it makes a lot of sense and it gives you a hell of a lot of performance in terms of your query processing. And I'll show you one example here since we are doing demos. If you notice here, I go to the DDL, the back sales table, distribution equals hash. So I'm using the online sales key. But then if I go to one of these smaller tables, like the currency dimension, you'll see that distribution equals replicate. Okay? So that's an example of it there. Okay. One other thing, and we're starting to get close to the end, guys. Thanks for sticking with me. One other thing I want to point out, and a lot of times my customers get these mixed up because before APS was created, a lot of customers were using partitioning to actually do distributions. So if you guys are familiar with sharding and spreading your data across servers, and a lot of times customers will get distributions and partitioning mixed up. And I want to be very clear here that distributions and partitions are separate concepts. And if we look here in this world of distribution and partitions still exist. We actually create partitions for each one of the distributions so that when a range query comes into the platform, not only are we running all these simultaneous queries across the platform, but we're actually doing range partitioning or dynamic partition elimination on each one of the distributions in parallel. Okay.
Were you keeping the distribution keys in the brain?
Yes. Yes. The distribution key, the metadata for the tables, that's all stored in the control. Okay, real quick on the physical architecture. So you guys got the logical architecture, you've got the data distribution, you're almost there. You pretty much got the lockdown on how the APS system works internally. Just to give you some of the feeds and speeds in terms of what we have underneath the appliance, we are using standard one-use servers like the Dell R620s, HP L360s, Hyper-V virtualization, dual socket, 8 cores each, 256 gigs of RAM. We have dual redundant networks. We're using InfiniBand, 56 gigabits per second for data movement. We're using Ethernet 10 gig and 1 gig. Number one, to connect into your data center, because we don't have too many customers that are using InfiniBand in their data center today, but also to do the management of the system as well. And then finally, we have our I/O subsystems. This is RAID 1 mirror, direct attached storage, using 2012 storage spaces to do the RAID 1 mirroring. You have the option of 1, 2, or 3 terabyte hard drives, and then each of these disk enclosures has 66 hard disk drives, and then hot spares. You can think of a hot spare like a spare tire. So if one of your disks goes down, you got the spare disk in there, and as soon as that disk goes down, this new disk actually starts rebuilding with that data. So again, fully redundant, and bringing in this box, and everything inside the box is mission critical, it's highly available. If you look at that box and what it looks like, you're going to have your networking at the top, InfiniBand and Ethernet. You're going to have your control host. This is also the control server, but we call it a host because we're using virtualization. Your failover host, so if any of the service goes down, it'll automatically migrate to the failover host. And then what we call our first scale unit. So what you're looking at now is your entry point into the APS appliance. Okay, this is the smallest footprint that we offer for our customers. It's what we call a quarter of a rack, only filling up with 2 of those compute nodes. And again, another differentiator for us, and this is very keen, is that we don't have this concept of disruption. When you get to a point where you hit a wall, you're running out of performance, you got to figure out if you're going to rip and replace the box or upgrade to the latest version and try to use the new features, etc. You just add another scale unit. When you add that other scale unit, the upgrade process is managed by us. You say, hey, we want to upgrade the scale unit, you give us some downtime over the weekend, we add the scale unit in, and we run the upgrade process. Remember that distribution of data I told you about? The data that's on this first storage unit, half of it automatically migrates over to this second storage unit as part of the upgrade. And when that data migrates over, now your data is spread across all the nodes, you have double the horsepower. And that's what I was saying, if you do your ETL and an ELT, you're actually doing the ETL processing in the database, you add in the second unit of scale capacity, and now your ETL time, if it was taking 6 hours, it should be roughly 3 hours, it's about 3 or 4 hours. So that's without any flow changes, or you're actually changing the way the system works. Yes, sir? No. Yeah, there will be downtime, absolutely. I mean, think of this as a major upgrade, right? I mean, it's a lot shorter than a major upgrade would traditionally be, but it still is an upgrade, so the system can't be online while it is. Great questions. And you can continue filling that up, all the way up to 8 nodes in a single cabinet, and then you have a little bit of white space there if you want to add in the BI or ETL server inside the cabinet, directly attached to the InfiniBand, internal network, all that goodness. Okay, I'm only going to keep you guys here for a few more minutes. I know it's getting late, but I'm going to end this session here with some more demoing, unless you guys want to hear about how Polybase works technically. You tell me. So let me get a raise of hands who wants to stick with the slides and learn how Polybase works, how the syntax is. And let me get so raise your hand if you want to see how Polybase works. Just one. But what about if you want to see a demo of Polybase as opposed to how it works? Okay. All right. I'm gonna try to do both. I'm gonna go with that. You guys can stay after if you want to understand more how this Polybase actually works, but I'm going to give you a brief overview. When we created Polybase, we wanted the ability for our customers to access data, and Hadoop can access data in the cloud without knowing that it's there. Okay, so we put an abstraction layer to basically say, we're going to let you use SQL Server how you use it today. Doesn't matter where the data is, write your query as you do, and it'll work. And how we do that is using some different abstraction layers to actually encompass the different platforms, file formats, and actual data that we're trying to go after. So the first thing that we have different than a traditional SQL Server is what's called external data sources. So this is a syntax or command that you can run in BAMBIUG. When you create an external data source, you give it a name, you give it a type of data source. This would be Hadoop, this would be Azure Blob Storage, etc. And then stay tuned because we're actually looking at extending Polybase to new platforms like maybe Oracle, maybe SQL Server, some other platform we can go out and reach to a query. You do the location of where the actual, in Hadoop's case, it's the location of the name node, the IP address of the name node. And then if you're doing the map reduce pushdown, where you're pushing down that computation, you can also point it to what's called the job tracker in Hadoop, where that's basically where it submits jobs for the process on Hadoop systems. The next layer of abstraction is what's called an external file format. And so what we saw is that, well, people are going to store data in a lot of different ways in the Hadoop platform. And so we wanted to make sure that we support the most common types of data formats in Hadoop platforms out of the gate. We certainly support text data, and you can load text data into the platform. You can have it also compressed so that data can be natively compressed on Hadoop HDFS, and we can pull it in and uncompress it on the fly. And we also support some specific Hadoop file formats. So if you're familiar with Hadoop, we support HiveRC files. That's a row, columnar, hybrid file format, and we also support pure files. These are more optimized file formats for storing data in Hadoop. And finally, we have external tables. So this is basically the counterpart to a regular table in SQL Server. It acts just like a regular table. You can query it, you can join it, you can give permissions on it. Our program managers call it a first-class SQL Server citizen. So you can use it just like you use SQL Server tables. But under the covers, the data for this table isn't actually in the BW database. base, the data for this table is outside somewhere else. And so you'll see here, when I define this external table, I give it a table name and I give it the column definitions like I do with a regular table. But then when I actually instantiate it and give that physical form, I'm pointing it to a data source, I'm pointing it to a file format, I'm pointing it to a location in HDFS. This can be a file, a single file in HDFS. This can be a directory with many files in HDFS. And again, Polybase will resolve that directory and say, hey, I see a bunch of files, I'm going to bring them together to query. And I'll do all that automatically. Finally, underneath all of this abstraction layer, so you see here we have our nice business user running the regular T-SQL query. The business user only interacts with an external table. Underneath that external table, you have that data source and file format that you created. And then you have your query engine, which under the covers is using an HDFS bridge. The key here, when we talk about the HDFS bridge, again, if you're familiar with Hadoop, is we're using the Hadoop HDFS API. We're talking directly to the data nodes. We are going right in there, the native form of access to Hadoop systems. We're not using all these new features coming out, Tez and Sharp and Hive and Spark. There's a lot of new technologies that are coming into Hadoop. I think it's still trying to figure itself out right now, but we wanted to go in and say we're going to go at the lowest level so we get the most performance data transfer. Okay? Okay. Now I'm going to show you guys the demo. This is a quick overview. Let me show you some cool stuff with Polybase. Okay. So we're going to come in here and you'll see that the syntax for creating a table is just like creating a regular table, but we have this new keyword in there. We can say external. And so if I'm dropping a table or creating a table, I'm going to use this external table command. So we see here I'm going to create this external table. It's the customer dimension, but I put an underscore Hadoop so we know that the actual data is in Hadoop. You have your data types and you have your column names. And then you'll see here when we define actually where the data lives, we're pointing this external table to HDFS, we're pointing it to the IP address of the name node, and then we actually have the path where the file exists in HDFS that we want to access. We give some options in terms of the file format, and we also have options in terms of reject type and reject value. So we give you options in terms of saying, we'll let every query run where at least 90% of the data is clean in Hadoop. If it's 80%, we'll cancel the query. But you as a leader, IT administrator, you can choose what that threshold is because we know, hey, maybe all the data in Hadoop isn't clean right away, and we still want to give access to that data for our business users to query. So you can have that level check inside of the table itself. So we have a table here. Let's go ahead and create it. Okay. So that got created, and we see it was just going out and putting a pointer to the file in Hadoop. And once that table is created, I can go in here and I can submit queries against the platform. So you'll see here that, yeah, it took a couple of seconds, right? We're accustomed to that millisecond response times in PDW. Well, actually, when I submitted this query, Polybase query engine said, oh, this table is actually in HDFS. It went out to the Hadoop cluster, and it sourced the data at the time of query submission. So not until I actually press the button to submit this query is it going out to the Hadoop system, seeing if the file is there, and then bringing the data back. And remember I talked about that data to schema virtualization. We did this intentionally. What we call dynamic mining is maybe the file's there, maybe the file's not. We're going to allow you to create the table regardless. And not until you actually submit that query are we going to go out and check where the data is, if the data is fresh, if the data is alive, etc. So obviously, yeah, it's going to take a couple of seconds or so because you got to bring that data in, right? You'll see that if we, run this against the regular customer dimension in the system, yeah, it comes back sub-second, but it's identical in terms of how the business user interacts with it. It's identical of how BI and ETL tools interact with it. And we can do all the regular things we do. I can look up a single row, and that will bring back a single row, and we can continue. Now, where it gets really interesting is where you say, back to some of the queries where you have business user queries, right? So we say, okay, we have this billion-row fact sales table, and we want to join against it, and we basically want to see, what are the different sales amount, cost, and profit that we did on the system. And you'll see here we're joining that building on back sales table against customer dimension, geography, date dimension, group size, etc. The beauty of this is with the syntax being identical is I can come in, I can write queries, I can change tables under the covers where that data resides, and the business user doesn't care what the data is, they just want to have access to it. And so what you're starting to see is we have this capability where we can really do these data mashups, where we go in and we're bringing data from Hadoop and we're bringing data from the relational database and we're writing all sorts of nasty queries against it, and it's in the syntax and T-SQL that we like. We're getting the results from it. So if you look at this query here, the business user has no idea what the data is. But actually, this is going to in customer Hadoop. And so every time this business user is running this query, it's going out to Hadoop, it's sucking that data back, and it's processing this query internally. So we can continue doing that. Just some other things to keep in mind is we do have the capability not only to bring data into the database, but we have the ability to actually export data to the database, right? And so if you have some applications here where you want to do the processing inside of the database and then you want to push data back out to Hadoop, you have that ability. You see here that I'm creating another external table and I'm defining where that external table lives, but I'm actually populating it with data inside of our database, right? I'm doing some stuff. So now you see that we have that ability to bring the data into the database as fast as we want. Okay? One other thing I'll show you guys, which I thought was really interesting, and for the folks that joined, who were here earlier in the night before we started the actual presentation, I was showing you those tweets, right, those live tweets. And what I was showing you there was a platform called Stream Insight from Microsoft. It's part of the SQL Server family. It does complex event processing, or CEP, where it actually runs tweets coming in real time, and then it runs it against a sentiment analysis engine, where it basically says, I'm going to look at this tweet, and I'm going to figure out if the person writing this tweet is happy, if they're kind of neutral, or they're sad, right? And so what we basically did is we said, we're going to take Stream Insight, we're going to have all the tweets coming in real time, we're going to run the sentiment analysis engine against that, and then we're going to have the sentiment data, the metadata about those tweets go into PDW, our relational database, and we're going to have all that detailed data, all that tweet text and all this stuff that I don't know if you necessarily want to store it in a database, it matters how much you're actually storing. We're going to store that in HDFS because it's cheaper and it can store a lot of big data. So what you're seeing here is I do select star against the tweet info table, and that comes back, you'll see that I have 2.1 million rows or so. And we'll run this guy. We'll run this. I will show you another nice little secret about APS is that you get a rich web GUI in terms of seeing the system. And you can run on the system and basically see all the queries running, what's happening in terms of the health of the system. And remember, it's a hardware-software. So you basically can see all the hardware components running. So really, this is a rich web GUI that allows you to administer the clients, find out if there's any performance or bottlenecks very quickly. And I can go in the system and I can actually see what were my queries. So the queries that are running against the system. Let's see if there's anything else on the box. No. Okay, so tweet details large. That's still 2 million rows, but you see that took 4 seconds instead of that 1 second. And the reason for this here is we're actually sourcing 2 million rows from Hadoop. So every time I submit this query, it's going out and saying, okay, I gotta get the data from Hadoop, and then I gotta bring it back into the system, and then I have to do the count start against it. So yeah, it's gonna take a couple seconds this time because it's sourcing 2 million rows. Yes, sir?
Just wondering if possible to do explain time.
Yeah, well, I can actually do even one better, which is this. Show you a nicer explain plan, which is if I go into my queries, this is the query I just ran, and then I can click on it, and then I can actually see the step plan for that query. I can see the start and end time for each of the steps. I can see the duration if I want to troubleshoot if there's a particular step where the optimizer made a bad plan. And if Usually you don't have to do that though, but some people like to get really deep in technology. So that's pretty much it in terms of the integration. Now, you see that since these are both regular tables, I can come in and I can join them. I can run a new query against them. Right now, I'm just looking at the sentiment data you see here. So this is what I was thinking of running. And I'm not going to show you the Father's Day stuff because it might be a little bit too emotional. But if you're really interested, I'll show you afterwards. But we did take tweets on Microsoft and big data and Hadoop and all this stuff. And it basically shows you here's the amount of tweets that we gathered, the negative tweets, neutral, and positive sentiment from those tweets. And you can go in, I mean, do some really interesting ad hoc type analysis. And this was just me here, messing around with queries and what kind of data we could get. But you'll see here that I'm joining that tweet detail large. This is the data into Hadoop, the detailed granular tweet data. And I'm combining it with the tweet info table, which is all the sentiment data. Then I'm saying I want to find tweets that have to do with Microsoft. I want it to be a sentiment score equal to 1, so it's a positive score. Greater than 0, that's a positive sentiment, they're happy. And then I want to find out all the different types of hashtags that have to do with Microsoft where people are happy in the tweets. And so what you'll see here is all the different tweets that I gathered and the hashtags associated with it. So you'll see, the first hashtag, okay, well, people hashtag Microsoft a lot, but then the second most prevalent hashtag when it comes to positive sentiment is extreme loony. You see the next most prevalent hashtag is E3, so actually when I was taking these tweets, it's around the E3 time. And as you go through this, you'll see other interesting things. So I thought this one was interesting. Can anyone tell me why the Clippers? I got all sports, but so I was taking the tweets and I was like E3 and IaaS and cloud and all these things that make a lot of sense for Microsoft as a company. But then I saw the Clippers. So anyone want to tell me what the Clippers was? Steve Ballmer. That's right. Thank you, sir. So, the power of this is really in what I'm showing you, right? We're exposing the data. Even myself, I'm not a business analyst, or I don't have a business objective in terms of analyzing this data, but it's now exposed through a natural SQL interface. It's very easy for me as a SQL user to be able to ask questions of this data. And now it's very easy for me to match up data from the different platforms. So I'm not adding an additional layer of complexity to the business users or the BI or analytic tools when we expose this data up for them to ask business questions of. And so the key value proposition Microsoft as a company is we want to deliver productivity in our platforms. And we feel that with this technology, it's really delivering the ability to go after big data and meet a lot of data warehouse challenges that we see in the space. And with that, I'd like to end the presentation. I'd like to thank everybody for spending time with me here on Thursday night.